Hello, everyone, and welcome to the Chem Lab. Today, we're looking at a chart that you are guaranteed to see if you take a course like AP Chemistry or college level chemistry, and you're mildly guaranteed to see it if you're in your first year of chemistry in high school, for example. And this chart has a fancy name. It's called a Maxwell-Boltzmann distribution. And what we're going to do today is we're going to get into what it is, what it does, what it shows us, and how we can interpret it in some types of intermolecular force and kinetic molecular theory type problems. So let's get into it. So just what is a Maxwell-Boltzmann distribution and what is it doing here? If we take a look at this example that we have in front of us, take a look at what's being plotted. We have number of molecules over here, and on the horizontal axis, the molecular speed in meters per second. So we're plotting molecular speeds and the number of molecules that might have that particular molecular speed. And these are, you can see a couple of curves here. They have characteristic shapes. You'll definitely see those curves in your chemistry travels. And so what's this one showing us? This is showing us oxygen at 25 and oxygen at 1000 degrees Celsius. Notice that they're different. Okay, it's important to note that when gases and their molecules are at a certain temperature, all of the molecules themselves are not going the same speed. Some of them are going very slowly, and others are going very quickly. But most of them kind of settle into some middle average, and it's a distribution: some low, some high, a bunch in the middle, and it has this characteristic shape. So the peak of this graph is representing that at 25 degrees Celsius, most of the molecules of oxygen are going just a hair over 400 meters per second, which is crazy fast if you think about it. That's like one lap of around a football field track, and that's in a second. That's how fast those molecules are going on average. Some are going very, very much faster than that, and some of them are just pausing for a moment because they need a break and a quick little rest before they get moving fast again. All right, but this is a typical shape. All right, so look what happens to the oxygen, the distribution when the oxygen gets heated up. Okay, first of all, two things happen. When molecules heat up, they move faster on average. So we can see that the peak has moved to the right to a higher average temperature, and that there's actually a lot more molecules going even faster than they were before, way up here at this edge of the graph. And so we get a flattening of the curve. And so it's really important that we understand two things. When the curve moves due to a change in temperature, the area under the curve has to stay the same. If we're talking about the same number of molecules, the area under the curve, the integration under the curve, needs to stay the same. So if this molecule, this whole mountain, widens out, it has to flatten out as well. So you're going to see anything shifting to the right has to be shorter in height, and anything shifting to the left has to be taller in height. But the area under the curve has to stay the same. So that's oxygen at two different temperatures. Let's take a look at another one. And I'm reviewing this because you're going to see these in the multiple choice questions we do, and I think a quick refresher is helpful. All right. This one shows four different gases at the same temperature. So we have oxygen, which is a very tall peak, nitrogen, a little more spread out, water vapor, a little more spread out, and here's helium really spread out down here at the bottom. And this is trying to represent equal moles, equal number of molecules. So the area under these curves would be the same, except that helium is much more flattened. And you might be wondering, well, why? Why is this one way wider and flatter than oxygen? And it comes down to the molar mass of the molecules, the size of the molecules. So at any given temperature, they have the same kinetic energy. Okay, the molecules have the same amount of kinetic energy. It's based solely on temperature. That's not based on which molecule it is. But the idea here is that lighter molecules for the same energy will move faster than heavier molecules for the same kinetic energy. In the same way that I could throw a baseball a lot farther than I could throw a bowling ball, because the bowling ball is much heavier, and for the same energy I put into it, it goes slower and less of a distance. Okay, lighter molecules move faster, heavier molecules move slower. And then if you change the temperature, these go back and forth. So let's take a look at a couple of quick questions, and we'll do a couple of pause the video moments as well in here. All right, here we go. Here's our Maxwell-Boltzmann distribution. All right. The graph above shows the speed distribution of molecules in a sample of a gas at a certain temperature. Which of the following graphs shows the speed distribution of the same molecules at a lower temperature as a dashed curve? Okay, so we got to think to ourselves, this is what it looks like at the beginning. If the temperature decreases, it's got to go to the left. The big mountain, the tall part of the mountain has to go to the left. And if we look at the four examples that are shown here, only one of them goes to the left. This one goes to the right. That would be a speeding up of the molecules, a higher temperature. This one is just less molecules because it's just a lower mountain at the same spot. And this one wouldn't work either because you're going to the right, but also if it goes to the right, it has to shrink in height along the way, and that's not right either. The only one that fits is this one, moving to the left, and it gets a little taller because it's kind of smushing in there and kind of stacking on top of each other, more molecules in that space. So that would be our answer for this first one. All right, we'll take a look at one more altogether. At standard temperature and pressure, a 0.5 mole sample of hydrogen gas and a separate 1 mole sample of oxygen gas have the same. What do we have? It's average kinetic energy, average molecular speed, volume, and density. Okay, so we have a half a mole of hydrogen, 1 mole of oxygen at the same standard temperature and pressure. So half a mole and 1 mole, this would have half the volume because it's got half the number of particles in it, so it's not the volume. They would not have the same densities because oxygens are much heavier than hydrogen, so the higher mass would give you a different density. And we got to narrow it down between these two. Will they have the same kinetic energy or molecular speed? Well, the thing is, you have to remember, you have to laser focus for this episode and life in general, that temperature gives you kinetic energy. It does not give you speed. They will have the same kinetic energy, but the hydrogens, being lighter, are going to be flying around like crazy, where the heavier oxygens are going to be taken a little more slowly and easily for the same amount of energy. So they will not have the same kinetic speed, molecular speed. They will have the same kinetic energy. So try to laser in on that idea. All right, your turn. Take a little pause the video moment. Here, I'll read it for you. 2 flexible containers for gases at the same temperature and pressure. Same temperature and pressure. One holds half a gram of hydrogen. The other holds 8 grams of oxygen. Which of the following statements regarding these gas samples is false? Take a moment, pause the video, and meet you back here in a couple seconds. Okay, so if you chose D, then you did a good job laser focusing in on the idea of temperature and kinetic energy. The kinetic energy will be the same. That's true. The number of molecules will be the same. This is 1/16 of the weight of this. So hydrogen is 1/16 the weight. So you'll have the same number of molecules and the same volume because you have the same proportional number of moles. The one that's the difference is the average speed. And now we're going to get into a couple of questions where we're comparing two different gases. Here we have one with two curves on the Maxwell-Boltzmann distribution. And it says the MB distribution of molecular speeds in samples of two different gases at the same temperature are shown above. Which gas has the greater molar mass? So at the same temperature, they have the same kinetic energy, but one of them is going to be moving slower and one of them is going to be moving faster. The one that is moving slower is going to be the one with the greater molar mass. So when you're comparing these two, the slower one has the heavier mass, and that would be A. The one that's moving faster on average would be the lighter or smaller molar mass. Both gases have the same. Nope, that's not it. And it can't be determined. Yeah, we can determine it because this one is farther to the left and moving slower. All right, so that's great. Here we have another one where we get to choose the Maxwell-Boltzmann distribution. And sorry about the tiny typing here, but the distribution of speeds of hydrogen molecules at 273 is shown in the diagram above. So that's hydrogen. Which of the following best shows the speed distribution of helium atoms under the same conditions? So we got hydrogen, we need to add helium. And so we have to ask ourselves, is helium heavier or lighter than hydrogen is? And helium is heavier because it's got a molar mass of 4, while hydrogen molecules, diatomic ones, have a molar mass of 2. So the helium atoms are going to be moving slower on average. So we are looking for something whose peak is to the left and also taller. So this one is to the right. Nope, that doesn't work. This one is pretty much the same. That won't work either. This one, again, is to the right, so that won't work. The only one that works, and we should double check. Yes, it's to the left, and yes, it is taller because we're kind of piling things up over to the left. All right, and it's our next pause the video moment. Here is a quick question. Based on the Maxwell-Boltzmann distribution at 300 Kelvin, which of the following gases could be represented by curve X? Take a moment, pause the video, and I'll see you back here in a couple seconds. Okay, and if you chose A, then good job on that one. We're looking for something because it's moving slower at the same temperature. We're looking for something with a higher molar mass than oxygen, and the only one with a higher molar mass than oxygen is bromine. The rest of these are lower than the molar mass of oxygen. So if you got that one, great, good job, and we're moving into our last. This last section is going to serve as a sort of public service announcement from me to you. And you might be wondering, why do we need a public service announcement? Well, let's take a look at a couple examples, and you'll probably see why we will need one in just a moment. 3 equimolar gas samples are at the conditions given in the following table. Assume all the gases behave ideally. So that's, all right, good assumption. And we have fluorine, nitrogen, oxygen, their volumes, their pressures, their temperatures. Which gas, if any, has molecules with the greatest average kinetic energy? Fluorine, nitrogen, oxygen, or they all have the same. And take a moment, see what you think. And as I'm looking at this thing, when they're talking about kinetic energy, the only thing I need to worry about is temperature. I don't need to know about anything else here except temperature. And look, all the temperatures are the same. And so therefore, I can just jump right to that one and not worry about all of this stuff that's over here. So again, laser in on the temperature and kinetic energy relationship. Now take a look at this one, an actual old exam question. We have 3 gases in identical rigid containers under the conditions given in the table below. Methane, ethane, butane. Formulas: molar mass, temperature, pressure. The average kinetic energy of the gas molecules is greatest in A, B, or C, or again, all the same. And if you're starting to get the idea that this one is similar to the last one, you're right. If you look at the temperatures, they are all the same. And therefore, they're the same in all containers. They have the same kinetic energy. They won't have the same speeds. Methane will have the largest speed because it's the lightest molecule, but its kinetic energy will be the same. Now, are you getting this idea that, man, there's a lot of information present in this question? They gave me a whole ton of stuff, a lot of distractors and a lot of noise going on, and they're going to do that. That's my public service announcement. You're going to see questions where there's a lot going on and a lot of distractors, but then you'll be asked about kinetic energy, and the only thing you need to worry about is temperature. Okay, so yeah, that's the public service announcement. Just try not to get distracted by everything. Here's another one with a lot going on. 2 liters of air, 5 liters of air. The volume of the sample of air in a cylinder with a movable piston is 2 liters at a pressure, P1. The volume is increased to 5 liters as the temperature is held constant. The pressure of the air in the cylinder is now P2. What effect do the volume and pressure changes have on the average kinetic energy, there it is, of the molecules in the sample? And you might have just glossed right over it, but guess what? The temperature is held constant. So, all this other stuff, this little diagram and, pressures and volumes and stuff, doesn't even matter. So the average kinetic energy is staying the same because the temperature stays the same. All right. Last pause the video moment of the day. We have a 1 liter sample of helium gas at 25 and 1 atmosphere is combined with a 1 liter sample of neon gas at 25 and 1 atmosphere. The temperature is held constant. Take a moment, pause the video, and find out which of the following statements about combining the gas is correct. Take a moment. See you back here in a couple seconds. And if you chose D because you've been paying attention and you're a smarty pants, excellent, because temperature is held constant. The average kinetic energy of the helium and neon atoms do not change when the gases are combined. So I'm hoping that you'll take my advice and keep that in the forefront of your mind. Don't get distracted by all the other noise that's out there. and focus on kinetic energy being proportional to temperature and laser in. I hope you found that helpful. If you have any questions, send them to me in the comments. In the meantime, happy studying and have a great day.